Relative motion going to be the topic of this lesson. We're going to start with some classical one-dimensional problems involving trains. And then we'll move on to some classical two-dimensional problems. And we'll see that just like we've done throughout the rest of this chapter on motion in two dimensions, we'll be able to treat the x dimension and the y dimension independently. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. All right, so let's deal with relative motion in this classical one-dimensional problem involving trains here. So we've got train number 1 heads west on a track with a speed of 30.0 miles per hour. Train number 2 is 150 miles behind train number 1 and heads west on the same track with a speed of 45 miles per hour. How much time passes before the trains collide if they maintain these speeds? All right, so this one you're probably, good chance you're reasoning this one out in your head. And you're like, well, train 2 is traveling faster than train 1. It will eventually catch it. And in this case, you might even say, oh, it's traveling faster by 15 miles per hour. So to close that gap of 150 miles, it's going to take 10 hours. So, and you probably just did something akin to delta x equals vt and solve for the time there. Delta x was that 150 miles. So v here was the difference in the speeds here, the closing speed, if you will, of 15 miles per hour. And then you solve for time. Now, you didn't realize it, but you were doing a relative motion problem because we didn't actually solve for any sort of absolute displacement, just the relative displacement between the two cars. And we didn't use either car's absolute speed. We used the relative speed of one versus the other. And so you were doing a relative motion problem in your head if you tracked that without even realizing it. So let's kind of realize how we're setting this up. So typically in a relative motion problem, so you're going to have one or two objects potentially. And then you might have some other reference frame, which is often the Earth in many of these problems as it is here. So for train number 1, we know its speed relative to the Earth is 30 miles per hour west. Train number 2, its speed relative to the Earth is 45 miles per hour, also due west. The question is, what are their speeds relative to each other? Well, it depends on how you're looking at it. In this case, what I want is the speed of train number 2 relative to train number 1. So maybe the speed of 2 relative to 1. And the way you do this is you take the difference as long as you know their speeds relative to some third reference frame, which in this case is, again, usually the Earth. And so in this case, signs are important. These both head west, and if you're putting these on a Cartesian coordinate plane or stuff, you might call these both negative, negative 30 and negative 45. In this case, they have the same direction, so I don't really care if you make them both positive or both negative, but I'm going to use that convention of making them both negative and just keep in mind that negative means west. So in this case, if I want train 2 relative to train 1, then I'm going to take 2 minus 1. And so negative 45 miles per hour minus a negative 30 miles per hour is going to get me negative 15 miles per hour for that velocity. We're going to multiply that by time, and then the relative distance here, displacement, relative displacement, is that 150 miles. Train 2 relative to train 1 has to close that gap of 150 miles also west, and so I'll also make it negative as well. Now notice we could have looked at, well, what's the speed of train car 1 relative to train 2, and then it would have been negative 30 minus a negative 45, and it would have been come out to positive 15 miles per hour. Well, for train 1, yeah, it actually, because that gap is getting smaller and smaller, it actually appears like it's going the opposite direction relative to train 2. But that's not what we needed here. We needed 2 relative to 1, and so it's 2 minus 1 for those velocities. And so in this case, we solve for that time, and it's just going to be the 150 divided by 15, and that's where we get those 10 hours from. Okay, so the even more classic problem is if the trains are actually heading towards each other, as in the example below. And so the numbers I'm using are exactly the same, but now we'll just have them heading towards each other. All right, train number 1 is heading east on a track with a speed of 30.0 miles per hour. Train number 2 is 150 miles east of train number 1 and is heading west on the same track with a speed of 45.0 miles per hour. How much time passes before the trains collide if they maintain these speeds? And this is probably like the penultimate classical physics relative motion problem here. So, and again, this is one you might reason out in your head. And if you've got a really good intuitive feel for this, you might just realize, Well, they're both heading towards each other with a combined rate of 75 miles per hour. And so to cover that distance between them of 150 miles, it's going to take 2 hours, Chad. No big deal. Great. If that's the level of understanding you have, fantastic. So in 2 dimensions, it might not be so intuitive. And so figuring out how to set these up formally has some value here. So a couple things to note. So these are not heading in the same direction. One's east, one's west. And so they're not going to have the same sign now like they did above. And so in a normal Cartesian sense, we might make east the positive x direction and call this positive 30 miles per hour. So, and west, we might say the negative x direction and call negative 45.0 miles per hour. And then we might set up the same kind of a calculation where we've got displacement equals velocity times time. So, and technically could be a delta t, whatever. And in this case, I'm going to do the same relative velocity of train 2 relative to train 1. And technically, we could do it either way. We could also do train 1 relative to train 2. But we've got to be careful how we define our displacement then as well. As long as I'm doing it velocity of train 2 relative to train 1, I should do the same thing for the relative displacement as well. So, because for car 2 relative to car 1, it looks like he's heading west. If I was looking at the relative displacement of 1 relative to 2, it looks like train 1 is heading east. And so the sign is going to change either way. Well, we know that displacement is 150 miles. The question is it positive or negative? Well, again, 2, what does it look like train 2 is doing relative to train 1? It looks like he's heading west, which will make negative. So that's negative 150 miles. And then the velocity of 2 to 1, and again, as long as you know what their relative speeds are relative to the Earth, you take the difference between the two. So, and in this case, if I want 2 relative to 1, then I take 2 minus 1. And so negative 45 minus a positive 30 is negative 75 miles per hour. And then we'll solve for time. And so 150, negative 150 I should say, over negative 75 is going to get us that time of 2 hours. And again, the trick is, as long as you know the speed of each car, in this case, relative to the Earth, you take the difference between those two to figure out what that relative speed is, one versus the other. All right, now we've got the classic 2-dimensional physics relative motion problem, and it's going to involve a swimmer trying to swim across a river that's got a current involved. And so if we read this, a 30.0 meter wide river is flowing east with a speed of 2.0 meters per second. A man swims with a speed of 3.0 meters per second relative to the water and attempts to cross from the south bank to the north bank by heading due north. How long does it take him to cross is the first part of a 4-part question. So we'll start with that first part first, but let's generalize some things here. So in this case, in the last example, we talked about having 2 train cars and we knew what their speeds were relative to the Earth. And if you know both of their speeds relative to the Earth, you can then find their speeds relative to each other. Well, this one's set up a little bit different. In this case, we know the speed of the water relative to the Earth, but we don't know the speed of the man relative to the Earth. We actually already know the speed of the man relative to the water. So it's a little bit different setup and stuff, but we'll find out that in treating it in 2 dimensions, we can treat the x dimension and the y dimension separately, like we've been doing all along in this whole chapter on motion in 2 dimensions. We'll kind of see how this plays out. So the first question is, how long does it take him to cross? Well, a couple things we should realize. So if we kind of look at this in kind of vector sums here, so he's trying to head due north. That's responsible for part of his motion, 3.0 meters per second. But the current's taking him downstream. And if we add those 2 vectors in kind of tip-to-tail fashion, so it's giving him an overall velocity vector relative to the Earth pointing off in that direction. So that's why he's not going to end up straight across on that north bank. He's going to end up downstream a little ways. Well, the first question just is, how long does it take him to cross? Well, in this case, for how long it takes him to cross, we're going to deal with just a single dimension here. We know the displacement in that y direction, if you will, the north direction, is 30 meters. So then all we need to know, well, what's his velocity in that direction? Well, fortunately for us, it's already kind of broken up into components quite nicely. So if we take a look at this in terms of x and y, and keep in mind x is kind of the east-west direction, and y is kind of the north-south direction. And we got 2 reasons for his motion. One is his own swimming. And in this case, he's trying to swim due north. Due north is in the positive y direction. So that's positive 3.0 and not in the x direction at all. That's his swimming. but the current from the water is in the positive x direction, the due east direction entirely. So that's going to be positive 2.0 and then 0 in the y direction. And so the two components of his velocity, what's nice is they're all already kind of broken up into components themselves, one being all y, one being all x. And we can figure out what that resultant vector velocity is if we need to. We'll see that's the third part of the question. But in this case, we don't need to. All we need is what is the overall x component of his velocity? Well, that's easy to see. The overall x component of his velocity, I just add them together, is just 2, because 2 plus 0 is still 2. Oh, actually, I didn't need the x, I need the y. The overall y component of his velocity is 3 meters per second, because 3 plus 0 is still 3. And so he's got to traverse a vertical displacement of 30 meters, and he's doing it with a y component of his velocity of 3.0 meters per second. So let's go ahead and solve this here. So we've got delta y is going to equal that y component of his velocity times the time. And I guess that's positive 30 meters, 3.0 meters per second times time. Divide through, we're going to get time of 10 seconds. And technically, I need 2 sig figs. I'm going to put a bar over that. I could also make it 1.0 times 10 to the first seconds, if you will, as well. So, but based on the numbers we got input, I need 2 sig figs in my answer. Okay, but 10 seconds. All right, not so bad. So just like we've been doing, again, we can treat the x dimension and the y dimension completely separately. And so we needed just the y displacement and use just the y component of the velocity to do that. Let's look at the second question. So how far downstream is he when he reaches the north bank compared to where he started on the south bank? And as we said, he's actually heading off in some direction here, off because of the two components of his motion here, or the two contributors to his motion. And so the question really is, he's not going to land right directly across. He's going to land downstream some distance. Well, how far? Well, we don't know. But if you notice, how far downstream he lands is the x displacement. And so what we're really being asked here is just to find the x displacement. Well, once again, if all you want is the x displacement, you can just deal with the x dimension. And now we just need the x component of his velocity and the time. Well, fortunately, we already now know the time, and the x component of his velocity is just the 2 meters per second, because 2 plus 0 is 2. And the time of the journey, we just figured out in the first part, is 10 seconds. And again, I'll put a bar over that 0 to make it 2 sig figs, but we can see that he's going to end up 20 meters downstream in the eastward direction relative to where he started. He's not going to end up, again, directly on the north bank from where he was on the south bank. Okay, that's question number 2. Number 3 is, what was his velocity relative to an observer on shore while crossing? Well, if we got an observer who's standing still on the shore, this is the same as saying, what was his velocity relative to the Earth? So, and again, we know the components, 3 in the y direction, 2 in the x direction, and so we can just use the Pythagorean theorem to figure out what that resultant vector is. And so in this case, we're going to get the square root of the x component squared, so 2.0 meters per second squared, plus the y component squared, 3.0 meters per second squared. So 2 squared is 4, 3 squared is 9, 9 plus 4 is 13, and the square root of 13 is 3.61. And I'm going to round it to 2 sig figs again, so 3.6. meters per second. But now we need a direction here. And if you recall, my standard way of finding that direction is tangent of theta equals y over x, or in this case, the y component of the velocity over the x component of the velocity. Now, we got to remember something here that's crucial, is when I defined kind of using this to find the angle theta here, you got to remember that theta was always defined relative to the x-axis. And so in this case, that's going to be this angle right here, theta, relative to the x-axis. Well, what you're going to find, though, is that oftentimes when we're not dealing with x's and y's, but with north, south, east, and west, they might actually ask you for the other angle instead. So, and it really depends on how they define it, or it really depends on how they report it in, say, a multiple choice question. So, but right now, we're definitely finding the angle with respect to the x-axis, not the angle with respect to the y-axis by using this formula. All right, so let's see how this plays out. So theta here is going to equal the inverse tangent of, in this case, the y component was that 3 meters per second, x component was 2 meters per second. So inverse tangent of 3 over 2 in parentheses there. And we're going to get 56.3 degrees, which I'm going to round to 56 degrees. Cool, but that's not very specific here because we'd want to say that that means 56 degrees relative to the positive x-axis. But again, when we're dealing with north, south, east, and west, there is technically no positive x-axis. Now, we might want to say that, well, east is kind of like the positive x-axis. Well, it kind of is, but that's not how we define the direction here. We've got to define it in terms of north, south, east, and west. Well, in this case, this direction, again, is somewhere off here. And it's customary to define that one of two ways. You're either going to say that this is so far above the east axis, i.e. so far north of the east axis, and that would be this angle down here. So if I say north of east, it means it's referenced to the east. So north of east, I should say north of the east. So how far above, how far in the north direction of east. But you could also define it east of north and say how far am I going to bend it to the east of the north axis. And so whatever you end that with, the of part, it's relative to that axis. So again, east of north, north is the axis. North of east, east is the axis it's relative to. Okay, so in this case, the angle we got of 56 degrees, well again, that's this angle right here, and we could call that north of east. But we could have also have called it, got the other angle here, instead in the east of north direction. Well, they're complementary, so they add up to 90, and so if we take 90 minus 56, we're going to see it's 34 degrees east of north. And the reason I bring this up again is because standard convention, we always find that angle relative to the x-axis, but again, how they define it on a multiple choice question, well, it might be more convenient, or more, I should even say more, just more common for them to have defined it, you know, in an area of the direction he was swimming, trying to swim versus was swimming, and the angle in between wouldn't have been the angle with respect to the x-axis, but relative to the y. And some people will teach you to solve this and say, well, in this case, because we want that angle instead, make it x over y. I hate that. So I get students who are super confused on that. And so if I just say, if you always use this formula, you always get the angle with respect to the x-axis. If you need the other one, then subtract from 90. Cool. So this could have been reported as 3.6 meters per second, 56 degrees north of east, or 3.6 meters per second, 34 degrees east of north. Potentially either of those could have shown up on a multiple choice answer. So but most likely it was the last one, the 34 degrees east of north. All right, so last question here, last part of the question. If he had wanted to arrive at the north bank directly north of where he was located on the south bank, what direction should he have swum? Okay, so he wants to end up directly north. He doesn't want to end downstream at all. And so instead of heading directly north here in this case, he's definitely going to have to head kind of a little bit upstream in a sense as well. And he wants to end up here. Well, if he wants to end up perfectly north of where he starts, that means his overall x component of his velocity relative to the Earth must be 0. So let's go back here for a sec here. So now it's not, his velocity is not only perfectly in the y, they're going to be x and y components. And if we define this angle, again, relative to the x-axis and just call that theta, then we might call the x component here 3, let's see if I can draw this correctly, 3 meters per second cosine theta, and the y is 3 meters per second sine of theta. Cool, the question is really what angles you need to head to make this happen. Well, the key is I need the x components to add up to nothing. His overall x component must be 0 if there's no overall x displacement in his travels. And so right off the bat, I know that this 3 cosine theta has to have a value of -2, 2 in the westward direction, if you will. And so if we take a look at that and set that up, we can say that 3 cosine theta equals -2 meters per second. Now we got to be a little careful here. So with that -2, So we find out what that angle theta is, because the truth is I might actually get the angle from the positive x-axis if I use positive and negatives. Now if I use absolute values, and then that'll allow me to just go for that reference angle, and that's another way to go for this. So let's take our calculator out here. So let's say we take the inverse cosine. Inverse cosine of negative 2/3 all in parentheses. So negative 2/3 is in parentheses. And we're going to get 131.8 degrees, which might be 132 degrees, give or take. And I might even round that to 2 sig figs at 130 or something like that. So, but that would be 130 all the way from the positive x-axis. So if I subtract that from 180, now I'm going to get 48.2 degrees, which again, I'll probably round to 48 degrees as what that angle is right there. And how would we define that? Now, the other way of going about this is just instead of using positives and negatives here, and just say, I'm just going to find the reference angle and use absolute values. I'm not worried about negatives and positives. Okay, well in that case, then it would have just been inverse cosine of 2/3. And if we take the inverse cosine of just plain old 2/3, we should just get the 48.2 degrees, which again, I'll round to 48 degrees. So, but again, we've got to define that angle a little bit better here in terms of north, south, east, west. Well, the angle we got here is this one right here. But again, because its overall motion is going to be perfectly vertical, we might be asked for this angle right here instead. Again, if it's a multiple choice question, they get to decide how they want that defined. Well, the angle we found is relative to west, and it's north of west. But you could also be asked west of north, and that might even be more common. And so again, if this one's 48, then this is the complementary angle, and 90 minus 48 is going to be 42. So no matter how you slice it, it's going to be 3 meters per second again, relative to the water, but the angle is either 48 degrees north of west or 42 degrees west of north. Now, if you like this lesson, then you might consider liking the video. Happy studying.